Okay, so today we are continuing with our LEQ for this activity or for this unit. The LEQ is how can I define, recognize, and compare rational numbers in multiple representations. And we are going to start in our Springboard books on page 59. Go ahead, pause, and open up your books if you need to. Within this LEQ, we are going to work on two different learning goals. Today's learning goal is differentiating or telling the difference between rational and irrational numbers. So today we're going to focus on learning our two vocabulary terms, rational and learning irrational. I want you to turn to your partner and I want you to say rational and irrational. Once you have said that, continue watching. All right, so still on page 59, now we're going to read about rational and irrational numbers. It says, many early mathematicians believed or thought that all numbers were rational. That is, they could be written as a quotient of two integers. Real quick, so if I hear this term quotient, the operation in math that goes with that term quotient is division. If I'm writing it on the screen, you should write it in your textbooks. So the operation with quotient is division. It's division of two integers. So one number divided by the other number. However, as early as the 7th century BC, mathematicians from India became aware of numbers that could not be expressed as the quotient or could not be expressed using division. Eventually, it became accepted that the square roots of most real numbers could not be expressed rationally. These numbers were considered irrational. All right, so you already know the vocabulary term square roots. The square root is this symbol right here. What this is saying is that the square root of some numbers cannot be expressed as the quotient. So a quotient right now, a quotient looks like a fraction. That's important to note. All right, so some examples of irrational numbers are the square root of 2 or pi. So if we were to type in, let's type in pi in our calculator. So we see this number pop up. However, if I am to Google the value of pi in my computer, I see that pi actually has all of these numbers. Okay, so if you're looking at my little search thing, it has all of those numbers. So what happened in my calculator what happened in my calculator? If this is the value of pi and it keeps going on and on and on, what did my calculator do? That's right, my calculator cut it off. So even though it's not written, I could say that this number goes on and on and on. So same thing now, it cut it off right there too. But again, we could say that it goes on and on and on, and we would use dot, 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 or an ellipses to show that it goes on and on and on forever. Now I'm going to go ahead and I'm going to put in my calculator the square root of 2. So square root of 2. And once again, I get a number, and it looks like it stopped, the calculator cut it off there too. But I'm going to go ahead and I'm going to Google it. Let's see, square root of 2. All right, so if I look at the square root of 2, it's another one of those numbers. So if I look at this right here, that number also goes on and on and on. It's 4, 1, 4, 2, 3, 5, 6, 2, 3, 7. It goes on and on and on. It never ends. It doesn't stop. If I also so those are what we call irrational numbers. So based on what you know about pi, is this the entire value of pi? We're going to say no. And then that's because the value never ends. Or pi, so that's a math symbol called pi, and that means that pi never ends. Endless pi. It's like a great Thanksgiving. So then we can also look at this here. The square root of 2 is that the entire value is the screenshot there, the entire value of the square root of 2. Once again, no. So here, these are both what we call irrational numbers. They're both irrational numbers. So now I'm going to try a different number in my calculator. I'm going to try the square root of 4. That's just 2. I'm going to try the square root of 9. That's 3. Then the square root, let's see, square root of 16. That's 4. So what do I notice about my perfect squares? You're right, my perfect squares are what we would call rational numbers. All right, so what is the difference between the decimal forms of rational numbers and the decimal forms of irrational numbers? So a couple things. They either end, rational numbers, just going to type this in. So rational numbers either end or show a pattern. Irrational numbers never end and show no pattern. So let's look at 1/3, for example. So when I say show a pattern, 1/3, so this number right here is written as a fraction. It has a quotient. It's written with that little division or that fraction symbol. It also never ends. Okay, it's also something that the calculator cut off. But I can predict every number after this one. Every number after this one's going to be 3. So this is actually still a rational number. All right, let's dive into this a little bit more. In your notes, I want you to draw a Freyer model, and I want you to label this first one rational numbers. And I want you, so let that take up the top half of the page, and then down here, I want you to do irrational numbers and let that take up the bottom half of the page. Okay, so rational numbers at the top half, irrational numbers at the bottom half. Great, so if I look back at my definition for rational numbers are real numbers that can be written as a ratio or fraction. So these are numbers that can be written as a ratio or fraction. So I want you to go ahead and add that into your definition. A couple characteristics. Okay, they have patterns in their decimals, or they have what we call ending or terminating decimals. So let's do a couple examples of this. One example would be 1/3. So that is already written as a fraction. My decimal for 1/3 is 3 repeating. Okay, or I could write that as a 3 with the bar notation to show that it goes on and on and on and on and on. Another example could be like negative, let's see, -4/3. Okay, because again, if I go into my calculator here and I do -4/3, I just have -1 and 3 repeating. It's still written as a fraction. It still has a repeating decimal. It doesn't matter that it's negative. Another example would be the square root of any perfect square. So the square root of 4, the square root of 9. So really the square root of any perfect square. All right, great. Go ahead and get those written down, then we'll talk about non-examples. So non-examples are things that cannot be written as a fraction or ratio. So pi, for example. So pi is 3.14159, and it just goes on and on and on and on and on and on and on. Or I could take the square root of anything that's not a perfect square. For example, the square root of 5 is not a perfect square. It's 2.36067977, and even though the calculator cuts it off, it is going to go on and on and on and on and on and on forever. It doesn't matter if they're positive or negative. So same here. If I did negative the square root of 10, it still is an imperfect square, so it's still not an example of a rational number. Here, I had a negative number. That's still rational because it can be written as a fraction. Great. So now we're going to move on to irrational numbers. And anytime you have a question, just pause the video and ask. Or if you need more time writing down your notes, just pause the video as you write down your notes. All right, so my definition of irrational numbers, according to the book, was real numbers that cannot be written as a ratio or fraction. So I want to point out, these are still numbers. So they're all real numbers that cannot be written as a ratio or fraction. It's not like they're fake numbers. This is not fake math. Okay, they're still real numbers. They just can't be written as in that fraction format. So the characteristics of these is a couple things. Their decimals have no pattern and never end. Okay, the other characteristic, so no pattern meaning they seem random. The other characteristic is that a lot of these are the square roots or the cube roots or anything like that of not perfect squares. So those are a couple of our big patterns for this. So it's really valuable to know your perfect squares all the way up to 12 or 144. All right, so now let's give an example. An example would be something like the square root of 11. Because when I go into Desmos and I type in the square root of 11, not the sign of the square root of 11. Once again, I get a number that doesn't end, and it just goes on and on and on, and there's no pattern to it. Same thing here. If I were to do like the negative square root of 140, I would get a number with no pattern to the decimal, 11,832. And that would still be negative. It doesn't matter if it's positive or negative, it just matters right there. So my non-examples would be all of my perfect squares. It's like the square root of 25, even if it's negative, is still negative 5. Okay, or the square root of negative 36 is still going to be, let's make that a positive 36. It's still going to be 6. Okay, so all of my perfect numbers or anything that's a fraction. So even something like 17 thirds, because I can still write that as a fraction and it has a pattern, then it's still that like 66666, and that's actually a 6. The calculator just rounds it up. So that's still right there. I know that these numbers right here don't have patterns because if it does, I can convert it back into a fraction. But these numbers right here have no fraction bar next to them. Therefore, I know that they're irrational. These are whole numbers, so that way you know that you can see that they are rational. I could write 4 as a fraction just by saying 4 over 1. So right now, you can use Desmos. That's totally fine. So you can pull up Desmos or open up Desmos for this part. But you have all of these cards, and you have different numbers on a card. I want you to decide, is it a rational number or is it an irrational number? So let's start with like this one right here, -1/4. First question, is that written as a fraction? So -1/4, it is written as a fraction because it's the same thing as saying -1/4. That's a fraction. So that would be a rational number. So I'm going to put that one in my rational number pile. Whereas here, the cube root of 9, in a calculator, I can go ahead and try that. So I'm going to do the cube root of 9. And that gives me this number right here, but I can't turn it into a fraction. There's no fraction button in the calculator next to it. I also notice that there's no real pattern to it. It just goes on and on and on and on and on. So I'm going to put the cube root of 9 under irrational numbers. Go ahead and sort through the rest of your cards. Check with the teacher to see if you're doing it correctly or if you have any questions. The difference between rational and irrational. And then there is an uploaded PDF that you can check your answers on. But I want you to do this first before you check your answers. Great.